Hey, this is Professor Kernler, and this is the next video in our Calc 3 sequence. We're looking at section 17.1, vector fields today. And I apologize in advance. I'm having some flickering issues with my video capture here, so if I get a little flickering, I'm probably not going to go back in and edit those out. Let's just jump right in. We're just going to have one video for this one. We're going to define here. We're going to try to look at what is a vector field and give a definition for that. Define that vector field. We're going to draw a vector field. And then we're going to look at something called a potential function, which will be a thread throughout the rest of chapter 17. First, recall gradients. If we have the gradient of this function f, that would be the partial derivative with respect to x, which would be 2xy squared, and then the partial derivative with respect to y, 2x squared y. Now what's interesting here is this is a vector. It's a vector. It's a 2D vector, but it's a function. It's a function of x and y. So we can call this a 2D vector valued function of two variables. Now what's interesting is we know the gradient is always orthogonal to the level curves. So this gradient, I mean, there are infinitely many level curves, and wherever you pick a point, there's a level curve through that point, and the gradient is orthogonal to the level curve there. So it's a 2D plot of infinitely many vectors that are orthogonal to the level curves. I'll scroll down here. We could do the same thing for a function of three variables. The gradient here, let's see, the partial derivative with respect to x would be yz. The partial derivative with respect to y would be xz, and the partial derivative with respect to z would be xy. And similarly here, this is a three-dimensional vector valued function of three variables now. And again, all of these are orthogonal to the level surfaces this time, though. So we're just going to say orthogonal to the level surfaces. So that's going to be important to remember, that this gradient, remember, is always orthogonal to the level curves if it's a 2D gradient, or level surfaces if it's 3D. But what we're talking about here is we have this gradient, and it ends up that the gradient is a function itself, and it represents infinitely many vectors, depending on what x and y are, or with example 2, depending on what x, y, and z are. Okay, so let's talk about that. Let's give a definition for a vector field, and then we'll talk about why we're talking about gradients and how this wraps in. So a vector field over a plane region R is a function of two variables whose outputs are 2D vectors. So this would be, we'll call it a vector field, and it's a function of x and y, and it's some function of x and y as the x component and a different function of x and y as the y component. So this is a vector function, a vector valued function. It's a function of x and y, and it gives you an x component and a y component, each of which may be functions of both x and y. And that's like the gradient above was an example of one. A vector field over a solid region, D, is a function of three variables whose outputs are 3D vectors. So you can think of some examples, and we'll talk about some of these force fields where you have some, like a magnetic force that's pulling in many directions, and each of the magnitude of that pull is the magnitude of a vector, and there's a direction for that vector. And then vector fields like wind or fluid speed and direction. Those are all examples of vector fields, velocity fields, I should say. Okay, so let's look at an example of a specific one and try to draw a little sketch of it. So this vector field is relatively simple. Notice it's a bold F, it's a vector, and it's a function of x and y, and it's y and negative x. So we're going to plot a few of them that have equal magnitude output vectors. We're going to plot a few sets. So if we want them to have equal magnitude, that means the magnitude of that vector would be some constant. So let's find the magnitude. Be square root of y squared plus negative x squared, which would be square root of x squared plus y squared. If we set that equal to some constant, like we want the magnitude of these vectors to be constant, we actually get a circle, right? X squared plus y squared equals c squared. So if c is equal to 1, we actually have the unit circle. And so on the unit circle, I should have really zoomed in here a little bit. Let's zoom in. On the unit circle, say we have the point 1, 1. The vector is y negative x, right? Y negative x. Oops, sorry. Off the screen there. Y negative x. So the x component is the y component. So we're going to go positive 1. And then, actually that's not on the unit circle. Here, this will be on the unit circle, 0, 1. So the y component is 1, so the x is going to be 1. We're going to move to the right 1. And y is going to be negative x, but x is 0. So that'll be just like this, just to the right 1. What if we go on the unit circle here, over here at 1, 0? The y component of that, or the x component will be the y coordinate. So the x component will be 0. The y component will be negative 1. So it moves down like this. If we go down here at 0, negative 1. The x component will be negative 1, the y component will be 0. It's kind of messing with you there, but again, we're swapping the x component of the vector is the y coordinate, and the y component of the vector is the opposite of the x coordinate. So again, it kind of messes with you there. So here we have negative 1, 0. The x component is the y coordinate, that's 0. The y component is the opposite of the x, that's actually positive 1. Right, so here we have, this is 0, positive 1, this is 1, 0, this is 0, negative 1, this is negative 1, 0. Those all have a length of 1. And you can pick another point out here. Say I pick one, say I pick this point out here, 4, 2. It's going to be a little harder to draw. So the x component will be 2, so I'm going to have to move right 2. And the y component will be negative 4. 1, 2, 3, 4. So that one will go like this. This is the vector 4, negative 2. So if you're based at the point 4, 2, the vector from there is 4, negative 2. No. 2, negative 4. 2, negative 4. The y component, the y coordinate becomes the x component, and then the opposite of the x coordinate becomes the y component. So that is an example, and there are infinitely many there. We can't draw all of them because there are infinitely many. We could do a software package. We'll learn how to do some of this in Maple. We can plot some vector fields, but it's not something we can draw them all by hand. That's just not possible to sketch them all by hand. Trying to find the right amount of zoom here. That's pretty good. Okay. Radial vector fields are a specific type of vector field. If the vector field is some function times r, where r is simply x and y, so out x and y from the origin. That's called a radial vector field. There's some specific ones we're looked at where the vector field will be that radial r divided by its magnitude to a power. And those actually look pretty interesting. You get the radial, not the magnitude. Can't divide magnitude by magnitude. That's not a vector. So if you divide that radial vector r equals xy and divide by its magnitude to a power, then you can do a little simplifying here. I keep wanting to do magnitude. If you take the r and divide by its magnitude, and then you'll have p minus 1 left. What you end up with here is r over its magnitude, which we know is a unit vector, and then multiplied by some r to the p minus 1, whatever that is, that ends up being the magnitude of the vector field. So an example of this, of a radial vector field, is Newton's law of universal gravitation, where you have a center, and then all of the field, all of the vectors are going into that center. It's gravity, it's pulling into that center. So that's radial. F here is the force between two objects, and there's some distance r apart. You could express the gravitational field between two planets that way. So what you can do is we'll just center one planet at the origin, and the other at some point, x, y, z. So then r equal to x, y, z represents the position of the second. Second, could spell. So you can imagine here you have your origin and you have your planet here. It's like a sphere, right, centered at the origin. And then you have some other planet out here that's centered at x, y, z. So the force between the two planets ends up being a magnitude, or a vector field, where it is g times mass 1 times mass 2. And then the way we're going to do this is we're going to say it's over the magnitude of the distance between them, and then times a unit vector, r over the magnitude of r. And it would be negative here in this particular case because it's pulling in toward the first planet. And so this is an example. Don't worry too much about how I developed all that. My point only here is just to illustrate that this gravitational field is an example of a vector field. It's a radial vector field. Okay, there's one other topic we need to talk about, and that is this thing called a potential function. That example one that we did, we had this function and we created its gradient, 2xy squared and then 2x squared y. That's one way to generate a vector field. In this case, we call the function that it started with, we called it a potential function. And the generated gradient field is called a gradient field. So not all fields are gradient fields. These are just some examples. If a field could come from some original, like the gradient of some original function, then you call it a gradient field. And the function that it could have started with is called a potential function. So the notation we have for that is phi in general. We don't use f of xy, we use phi. So phi is some differentiable function, either on a two-dimensional region or a three-dimensional region. The vector field f, which is the gradient of phi, is called a gradient field, and that phi is called a potential function. And again, this potential function idea will be a thread throughout the rest of this chapter. So let's consider the potential function phi of xy is the inverse tangent of xy, and let's find the gradient field. Let's see, that'll be the derivative with respect to x. The derivative with respect to, we'll say u of tangent inverse of u is 1 over 1 plus u squared. So this will be 1 over 1 plus xy squared, but then I have to take the derivative with respect to x of the xy, so there's a y. And then similarly, the derivative with respect to y, 1 over 1 plus xy squared, but then I have to take the derivative with respect to y, and that would be x. So simplifying this, we get, scroll down a little bit, y over 1 plus x squared y squared, and then x over 1 plus x squared y squared. So that's the gradient field. We're going to talk about one last thing here. We're going to sketch some level curves. This is something that we'll talk about more. In this context, they're actually called equipotential curves, because the level curve, right, is when you're holding your function constant, but here we're going to hold the potential function constant, that phi function constant. So those are equipotential. And we're going to try to draw some of the vectors from the gradient field along the level curve. So the level curve, the equipotential function, I don't know which pronunciation is correct, would be when that phi function is equal to a constant. So that's the inverse tangent of xy is equal to a constant. Let's take the tangent of both sides. Xy is equal to tangent of c, and then tangent of y will be equal to tangent of c over x. So that's a hyperbola, and what the hyperbola looks like depends on c. Let's pick an easy one here. Let's pick c equals pi over 4. Then y would be 1 over x. Or if c equals negative pi over 4, y would be negative 1 over x. Let's draw those. Let's see if y, this is when we kind of have an ugly graph here. We need a little bit bigger. We're going to call this 1, call this 2, call this 1, call this 2, negative. It's just a little too small here, and I thought I had fixed that, but apparently not. Negative 1, negative 2. Okay, so for c equal pi over 4, y is 1 over x. So we have 1, 1, 2, 1 half, 1 half, 2, etc. So it looks like this. And then similarly on the other side, negative 1, negative 1, negative 2, negative 1 half, negative 1 half, 2. Okay, goes through something like that. That's c equal to pi over 4. Let's switch colors. Let's do red. For c equal or y equals negative 1 over x, it would simply be reflected here. And this is for c equals negative pi over 4. It would simply be a reflection. Sorry, I should scroll down there. And want to do something like that. Okay, now let's look at our vector field and let's graph a few vectors from the vector field. Like for example, we have this point 1, 1, and our vector field was, where did that go? Y over 1 plus x squared y squared, and then x over 1 plus x squared y squared. So let's try that at 1, 1. Let's see, it would be 1 over 1 plus 2, so 1 half, and then 1 over, so 1 half, 1 half. And if you look at this, watch this, if we go to that point and go 1 half, 1 half, it's kind of small, 1 half, 1 half, you'll see orthogonal to the level curves, right? Remember, the gradient is always orthogonal to the level curves, and since our curve is technically this potential function is really a function, and our gradient field is the gradient of that function, all of these gradients from this field should be orthogonal to all of the level curves. We could pick another one. Let's pick one on the red curve. Let's pick, how about 2, negative 1 half. So there, f would be, let me see, let's go where I can see, I don't have to move my head. 2, negative 1 half. So negative 1 half over, trying to do this in my head, negative 1 half over 1, oh, this is a bad idea. So y is negative 1 half. We have 1 plus, oh, is that just negative 1/4? Because we have negative 1 half over 1 plus 2 squared times negative 1 half squared. So that's just 1. And we have negative 1 over 2. So yeah, negative 1/4. And then x 2 over, let's see. Oh, that's going to be 2 over, so it's Okay, boy, I don't know, it's making me nervous. -1/4. So x here goes, the y goes up 1, x goes back -1/4. Not much. Oh, yeah, okay. Okay. That looks orthogonal, right? The y goes up 1, the x goes back a little bit, -1/4. Seems orthogonal. I don't know if we need to do another one. Let's try -1/1. So y is 1, 1 over 1 plus 1, that's 1/2. This one went here, sorry, whoops, sorry. That one was here. Here for, what were we doing? -1, 1. 1 over 1 plus 1, and then -1 over 1 plus 1. So 1/2, -1/2. 1/2, -1/2. Yep, orthogonal again, just in the opposite direction. It's interesting that the blue ones, the ones in quadrants 1 and 3, I think are going to go out. And the red ones, the ones in quadrants 2 and 4, I think are going to go, they're going to go the other direction. So that's kind of cool. So those are just some examples of, this is an example of a field, and you'll notice that because it's a gradient field, all of these vectors are orthogonal to all of the equipotential curves. All right, we'll talk a lot more about vector fields, a lot more about gradient fields and potential functions as we progress through this chapter, but that is it for this video.